So for section 5.2, we're really just continuing the ideas that we talked about in 5.1. So when we were talking about if you integrate a rate, you get an amount. We're just going to talk about some specific cases. So for example, if I integrate velocity, well, velocity is the rate of change of position, and so then that will give me the amount of change in position. So that's just change in position, right? I take the antiderivative of velocity, its position, and evaluate on that interval. We have a specific name for that change in position. It's called net distance or displacement. So most often you're going to hear it as displacement. So that's just how far removed you are from your starting point. If your velocity is positive, then that will also be your total distance. But if your velocity is not always positive, then you really want to focus on this equation here, the integral from a to b of the absolute value of velocity. That's total distance that the particle travels. And so whenever a problem asks you to find total distance, you always want to set it up that way, whether or not if the velocity is positive. Just to start out, set it up that way, and then you can analyze from there. So let's get into our first example. All right, so we have the velocity of a particle that is moving along the x-axis is given by this function, v of t equals 3t squared plus 6. All right, so it gives me the position of the particle at 472. What is the position at t equals 2? So let's write that out in terms of our equations. P of 4 is 72. Sorry, not question mark there. That one we know. The one we don't know is P of 2. P of 2 is blank. And so since we're only given velocity, we know that to get from velocity to position, I'm going to have to find the antiderivative. So just like we were doing in 5.1, we're going to set up a definite integral. So our definite integral of the velocity, and we're going to use those two x values, 2 and 4. That's equal to P of 4 minus P of 2. Always top minus bottom. And so then I actually want to calculate that integral from 2 to 4 of 3t squared plus 6. So I'm going to take the antiderivative of that. So that's t cubed plus 6t from 2 to 4, which is 64 plus 24 minus 8 minus 12. And that will give us 68. So that's what our P of 4 minus P of 2 is equal to. So let's actually write out up here that equation. 68 equals P of 4. We know that's 72 minus P of 2, which is what we're trying to find. And so then to solve, we're going to subtract 72 from both sides. Negative 4 is P of 2, negative P of 2. And so our P of 2, our position at 2 is 4. It doesn't have any units in this problem, and so we can just stop right there. We don't need to worry about that. In part B, it asks us something different. It asks for total distance. And so remember that the total distance formula is the integral from 0 to 7. That's our interval here. And it's always going to be absolute value of velocity. So specifically, we're going to plug in our velocity equation. One thing I want to point out is that absolute value is inside the integral. So I'm integrating the absolute value function. It is not the absolute value of the integral. So that means I need to consider that 3t squared plus 6 and where it's positive and negative. So if you think about what that graph looks like, you know it's quadratic and it's shifted up 6. So when I think about that parabola, it's always positive, which actually means I can take off the absolute values because it's already always positive. And so then I can use my same exact antiderivative as before. I'm just on a different interval. And then evaluate. 7 cubed plus 6 times 7 minus 0 cubed minus 6 times 0. And that will give us 385. Okay, let's try a more complex example now. just with a velocity equation that's a little bit harder to deal with, we will be using our graphing calculators for this one. All right, so same idea. We have velocity. It's given by this equation here, 0.5 e to the t times t minus 2 to the third. So we know the position of the particle at 1.5 is 2.551. It's asking for the particle position at 3.5. And so we'll set it up the same way. Integral of v of t dt. We'll do it from 1.5 to 3.5. And that's equal to p of 3.5 minus p of 1.5. We know that's 2.551. And so what I can say is, if I solve for this p of 3.5, it's just going to be 2.551 plus my integral from 1.5 to 3.5 of 0.5 e to the t times t minus 2 cubed. And so that way I can type that into my calculator all at once. Make sure that 2.55 is out in front of your integral, not afterwards. Otherwise, you might accidentally type it inside your integral. So if you calculate that, you should get 18.470. For part B, we're again talking about total distance, which means I'm going to be doing the absolute integral of the absolute value of velocity from 1 to 5. And so in my calculator, I'm going to type the integral from 1 to 5 of the absolute value of 0.5 e to the t times t minus 2 cubed. And since I'm using my calculator, I don't have to worry about where this function is positive or negative. My calculator is going to handle that for me. So I can find the absolute value symbols. If your calculator is updated, it's alpha and then window. And you're going to hit the one that says ABS for absolute value. And that will insert absolute value formulas. Your other option is if you go to math and then over to number, you'll see it there. All right, and so then I can just type that in, and when I calculate it, I will get 913.067. Please make sure you're taking the time to type this out in your calculator and make sure you're getting the same answers I do, just so you know how to actually put them in the calculator. All right, let's go on to a graphical example now, instead of these algebraic examples. All right, so in this next example, we have a graph of velocity measured in feet per second. So we see these units, we're going to probably use that. Of a particle along the x-axis. We know the position of the particle at 8 is 12. Go ahead and write that as an equation when you read that in the problem. And we've got this graph of v of t. So it asks us for the position of the particle at 3. That's going to be the same kind of setup we've been doing. P of 3 equals question mark. And so I know I'm going to integrate velocity from 3 to 8. That will give me my position at 8 minus my position at 3. So when I have a graph, if I want to find my integral, I know that's going to be the area under the curve. So I'm going to go from 3 to 8 and find that area. It's probably easiest if you split this into a rectangle and a triangle right there. So this is 5. This is also 5, just half base times height. And this is half base times height as well. So that's 2. But since it's below the x-axis, it's negative 2. So for my integral from 3 to 8, I have 5 plus 5 minus 2. P of 8 I know was 12 minus P of 3. And now I get to solve this equation. So I have 8 on this side. I'm going to go ahead and subtract the 12. That's negative P of 3. So I have negative 4 equals negative P of 3. And so my position is 4. And really I should put my units on there. And so remember that if my velocity was in feet per second, my units for position would be 4 feet. All right, part B, what is the acceleration when t equals 5? So remember that acceleration is the derivative of velocity. So I want to find, if I want to find a of 5, that means I find v prime of 5. Make sure you actually write out that a is equal to v prime. So for the AP test, you want to make sure that the reader knows that you know that velocity's derivative is acceleration. So when I'm looking on the graph, v prime of 5 means slope of v at 5. And so I'm going to look on my graph over here. I see this, my graph at 5. My slope then, I can just use the endpoints. So I've got the point 4 comma 5 and then 6 comma 0. So change in y over change in x, 5 minus 0 over 4 minus 6. So that's going to give me negative 5 over 2. Thinking about the units here, remember we had velocity on the top, time on the bottom, so that's feet per second. Or if you want to write it the way we see acceleration a lot of times, just feet per second squared. Either of those will be acceptable. All right, part C is asking about net distance. That means displacement or change in position. So to set that up, I'm going to integrate from 0 to 10 my velocity. So that means when I'm looking at this graph, I'm just finding the area from 0 to 10. I can use symmetry again. Those are all 5. This is negative 2. And so my area will be 20 above minus 4 below. That will give me 16. And because this is in regards to position, or because I'm taking the antiderivative of velocity, these units will just be feet. Remember that velocity was feet per second, and so then I take off the per second when I am finding that antiderivative. Okay, part D says total distance the particle travels from 0 to 10. And so that's, again, the absolute value of velocity. And so then what I have to pay attention to is whether this is positive or negative, whether my velocity is positive or negative. So if I look back up at my graph, I see it's positive from 0 to 6, and then it's negative from 6 to 10. So I can split up my integral. Now this is going to be more complicated than what you really need to do, but I want to set it up for in case you have a more complex problem. I can integrate the positive part normally, just 0 to 6. But on the part where I'm negative, if I'm going from 6 to 10, if my velocity is negative on that interval, to make it positive, I would do the opposite sign. So I'm going to subtract the part where it's negative. So this area up above is 20, and I'm subtracting the area below, which was negative 4. In other words, I'm really just adding on that area instead of subtracting it. And so I have 20 plus 4, and I get 24. So you could probably do that easily without rewriting this integral here, because on a graph you can see where it's negative. But if you had to do it algebraically, you would have to show that integral change. All right, we're going to pause right there and go to the next video for the rest of the notes.